As we've seen, atoms and molecules are very tiny little pieces of matter. And so we cannot observe them directly. Thus, in chemistry and physics, we need to find a way to look at those very small objects. And the way that we do that is to interact them with light. So it is important that we understand the nature of light. Light is a wave, and so we need to understand the characteristics of waves. Let's start first by thinking about waves in water, which you're a little bit more familiar with. So if we turn on a faucet and let water drip into a body of smooth water, each drip will send out, will create a wave. And so you can see that this wave pattern, this repeating up and down undulation of the smooth water surface is what we call a wave. You're familiar with this if you've ever been to the ocean or if you've ever dropped pebbles into a smooth pond. So if we look at this instead from the top, each drip sends out a circular wave pattern if we're looking down on the top of that smooth body of water. This wave has a couple of characteristics. It has a wavelength, the distance between one top of one wave and the top of another wave, right? So the distance between these high points in the water, and that's called the wavelength. And then we have how many waves cross a certain point in a certain amount of time, and that's called the frequency. Or we could count the time it takes for one crest to the next crest to pass a certain point. And so we have several things that we can talk about with waves. We have the wavelength, which we typically give the symbol lambda, which is the small Greek letter for L. So the wavelength is the distance between crests on the wave. So wave crests. And then we have the period, which we often give the symbol tau, and that is the time between when crests pass a particular point. And the other way we could talk about the period is to talk about the frequency. So the frequency, we give the symbol nu, which is the Greek letter for N, and this is the number of crests that pass a point in 1 second. So those are the characteristics of waves that are important. We can measure the distance between crests. So let's pause this. If I put this little tape measure dot on the top of one crest and go to the top of the other crest, we can see that this wavelength is 2.3 centimeters. So we could measure from top of one crest to the top of another crest, and we could get the wavelength. We could also measure the period. So if we start the timer right when one crest hits this plus here, or maybe this plus here, that's a little bit easier to see. So if we hit the timer right when a crest passes this, and we time until the next crest passes that, we can get the period. And stop. So 1.59 seconds was the period for this particular wave that we've got going on here. Notice that the units, remember when we're making a measurement, we always have a number and we have the units. So notice that the units for this wavelength has units that are distance units. So in this case, it was centimeters. So it could be meters, it could be nanometers, it could be millimeters, it could be any distance measurement. And notice that the period had units of time, so units of seconds. So if I want the frequency, remember, is the number of waves that pass in 1 second. So I want the number per second. So this is the seconds per wave, right? So this is seconds per wave because it's per one wave passing a given point. So if I want the number of waves per second, I would just flip this over, right? So if I can think about what the units are, then I can figure out how these two things are related because their units have to be related. And so the frequency would be 1 over the period. And so if I take 1 over the period, 1 over 1.59 seconds gives me 0.629 per second, or waves per second. So the frequency is simply just 1 over the period. So water waves are disturbances in a smooth surface of water. Light waves, on the other hand, are undulations or periodic patterns in the electromagnetic field that is all around us that we can't see or feel or hear. So there is this electromagnetic field, and if we have a disturbance in that electromagnetic field, that's what we see as light. So let's look at light waves. So if we take the equivalent of the faucet that's putting drops in the smooth surface of the water, let's take and turn on the light, which causes undulations or patterns in the electromagnetic field. What we're most interested in actually is the electric field and not the magnetic field. And so what we're going to look at here is simply just the electric field. So we'll use our little measuring instrument here, take this guy off, and look at the pattern that we get as we get this undulation or this disturbance in the electric field. So the electric field amplitude goes up and down in this periodic pattern that looks like a sine wave. Just like the water went up and down in a periodic pattern that looks like a sine wave when we drop a pebble or put a drop of water in that smooth surface of water. So what we're doing is we're making a disturbance in the electric field so that the electric field amplitude goes up and down. So you can see that this electric field, this light, has the same sorts of characteristics. We have a wavelength, and we have a frequency, and we have a period. Okay, so the frequency, or let's do the wavelength first. So let's pause this, and let's measure the wavelength. So we go from top of one crest to the top of the other crest, and we get about 470.1 nanometers. So you can see that this wavelength is much, much smaller than the wavelength of those water waves. Remember that nano is 10 to the minus 9 and centi is 10 to the minus 2. And so we have a wavelength here for this particular light. We have a wavelength of 470.1 nanometers. So it's still in distance units. It's meters is the base unit, so it's a distance, but it's nano, so it's times 10 to the minus 9 meters. 470.1 times 10 to the minus 9 meters. Okay, so if we measure the period of this wave, so let's pull out our little stopwatch and let's see if we can measure the period. So what I'm going to do is I'm going to use this guy, and when a wave passes that, I'm going to start the meter. So when the wave passes this, I'm going to start the meter, and when the next wave crest passes, then I'm going to stop the meter so that I can get the period for this wave, just like we did for the water waves. Okay, let's take a couple of measurements here. Start, stop, 1.75. Let's try that again. Start, stop, 1.6. Start, stop, 1.83. Okay, so let's do some averaging here and get a value. So when I add up those values and divide by 3 to get the average, I get 1.73 seconds. Sorry, femtoseconds. These are all femtoseconds because that measurement is in femtoseconds. So that means that the period is equal to 1.73 times 10 to the minus 15 seconds, because 1 femtosecond, femto is 10 to the minus 15. So if I replace the F for femto by times 10 to the minus 15, I get the period in seconds. If I want the frequency, I will need to take 1 over this value, and the frequency is then 5.79 times 10 to the 14th per second. So when I take 1 over this number, I also have to take 1 over the units, right? And so you can see that the frequency of this wave is very, very large because there are lots and lots and lots and lots and lots of waves that pass this point in 1 second. We talk about the speed of light as we give that the symbol c, and c is 3 times 10 to the 8th meters per second. So notice that the units of this are meters per second. So if frequency has units of per second and wavelength has units of meters, then I can get meters per second by taking the wavelength and multiplying by the frequency. Because if I take the wavelength and I multiply by the frequency, so the wavelength in meters, the units will be meters, frequency is per second, that will have units of speed. So the speed of light is equal to the frequency, the wavelength times the frequency. That is true for all light waves. So if I know the frequency, because the speed of light is a constant, if I know the frequency, I can find the wavelength. And if I know the wavelength, I can find the frequency. I just have to do the algebra to solve for the variable that I'm interested in. So if I want the frequency, I divide both sides by the wavelength. If I want the wavelength, I divide both sides by the frequency. So now we know a handy relationship that the speed of light is the wavelength times the frequency of the light. It turns out that light has energy associated with it. And so light waves have, or any wave has energy associated with it, but light waves in particular have energy associated with them. And it turns out that the energy of a light wave is related to the frequency by another constant, which we give the symbol h. And if we take h times the frequency, that will give us the energy. So E is the energy of the light wave. So the energy supplied by that wave. And h is a constant which we call Planck's constant, because that's the guy who came up with it. And Planck's constant is equal to 6.626 times 10 to the minus 34 joules times seconds. And then frequency, we know is the frequency. And so you can see that if we take Planck's constant, which has units of joules times seconds, and multiply by the frequency, which has units of per second, then the energy will be joules times seconds divided by seconds. So the seconds divide out, and we are left with joules as the unit of energy. So energy is typically in in SI units, energy is in joules. Joules is a derived unit, and it's made up of mass, kilograms, distance, meters squared, and time per second squared. So the base units for a joule are kilograms meters squared per second squared. These two simple equations, which describe energy, wavelength, and frequency of light, are very important as we move forward, and you should just simply memorize those and know them. You don't need to memorize the constants, so you don't need to memorize the value of C or the value of H. You'll be given those. But you need to know these equations, and you need to be able to use them to find frequency from wavelength or wavelength from frequency and energy from frequency.